Okay, first of all, guys, thank you for bearing with me through like 4 grueling days. No one's listening to me. Shush. Thank you. That's as far as I got. Okay, guys, thank you for dealing with 4 consecutive days of lessons. It's a lot of me to ask. I hope that I've done a good enough job of explaining why I'm teaching it the way I am. I find the curriculum very frustrating because yesterday would have been where the 20-1 should really stop. And to me, it feels like a random smattering of just I teach you about these exact triangles, I show you how to plot them on a graph, I show you a few random things, but I don't think you get the whole big picture. Okay? So I know grade 11s, this is not actually your curriculum, okay? But I figure there's 2 advantages. One, hopefully it gives you a sense of why we just did all the other random stuff we did. And 2, you guys are going to be in their spot next year anyways, so I don't think it hurts for us to do one more lesson. Is that reasonable? So here's what I'm going to promise you. What I'm going to show you guys today, if you're in 20-1, I will not put on your tests, okay? Because it's not fair. It's not actually a curriculum. But I still think it's worthwhile for you guys to see like the whole point of what we're getting to. Okay, so you guys know this is on your tests, obviously. So, okay, at the partway through last day, I showed you guys this slide right here. Our goal now, after all of that like background info we did, is to try to be able to solve an equation. Okay, and so if I were to give you an equation such as this, there's 2 ways you could solve it. I can give you x and you solve for y, or I can give you y and you solve for x. And you guys should all have some experience with solving equations. This one right here, for example, if I tell you that x is equal to 1, you'd tell me that y is equal to 1, 2, 3, 4, 5, 5, 6. 6. Does that make sense? But if I tell you that y is equal to 0, there's actually 2 answers. Right? And you would actually use the quadratic formula, and by the time you're done, you'd hopefully get those as your answers. This is what we're going to try to build these skills towards, but we're going to do it with trig equations, sine, cosine, and tan, and so on. Okay. So today's lesson is really where the break between grade 11 curriculum and grade 12 curriculum comes in. Okay. Grade 11s, I should be able to ask you to do something like this, though. This is where we finished last day. Why don't I do one of the examples I didn't cover here? Just as a kind of a review before we move in. This would be expected, but then the next half is actually not. So, which one didn't I do? Did I do the tan one? Okay, why don't we do this tan one here as a group? So, tan of 3 pi over 4. First thought, what the heck does 3 pi over 4 really mean? Well, hopefully as you get more and more used to it, it's a new way of measuring angles. And I mean, hopefully it makes sense as to how it works, but I get it if it takes a little while to interpret it. The whole idea is that you're going to break your grid here up into quadrants and break it up into quarters. So this would be the first pi over 4. 90 degrees would be the second pi over 4. Over here, here's the third pi over 4. And flat across would be the fourth pi over 4. Hopefully you're getting a little more comfortable with that. And the angle we're looking for is all the way around to here. But what often helps us to do instead is let's make ourselves a reference angle triangle right here. So now we know where we're talking about. Next thought, we need to know what this actual angle is. Not in radians, but preferably in degrees, because degrees is a little easier to work with. So if I were to take 3 pi over 4 and multiply it by 360 over 2 pi, this should now tell me how many degrees it is. And you may already know this. It's 135 degrees. The more you do it, the more familiar you'll get. The reason why I didn't even need to do the math is that I knew that if this was 90 right here, and I break it into quarters, wouldn't this be 45 degrees? Wouldn't this be 45 degrees? Wouldn't this be 45? Wouldn't this be 45? You guys kind of like piece that idea together of breaking it up into fractions. So the last thing we need to know how to do is what are the sides on a 45-degree triangle? 1, 1, and root 2, yeah. Except one of those sides is incorrect because of the fact that I'm in a new quadrant. The new quadrant means that this one here has to be -1, just because it's going backwards. Last thing we got to do, tan is equivalent to opposite over adjacent, or in this example right here, the coordinate points would be -1 and 1 if I put like a point up here. in the corner. Tan is equal to your y value divided by your x value. So negative 1 divided by 1 should give you negative 1, hopefully. Let's try it. Go to your calculator. What tan is asking you to do is tell you what is the ratio of your opposite to your adjacent. So if I do tan of 3 pi over 4, and we make sure we're in radians, the answer was negative 1. How do you guys feel? Is that something that as we're doing it more and more, you're getting better at it? Because that's actually kind of like the first time that I can give you something to do, if that makes sense. I'm going to give you an equation. I'm going to say, if I give you an angle, you tell me the equivalency. So sine of 55 degrees equals what? Tan of 3 pi over 4 equals what? Okay? Does that make sense? Okay, here's where the divide is then. This is where 20-1 kind of stops, but 30-1 goes on. What we want to then try to work on next is, what if we're going the other way? What if I tell you that sine of theta equals 0.5? So I'm not telling you the angle. I'm saying, I'm going to tell you what the relationship is. You tell me what the angle is. And this is a huge, huge dilemma, because since we don't know sine, one of the things we can do is we can do sine inverse. And you've already learned how to do this, I think, at some point in your lives. If you do sine inverse of 0.5, it'll give you an angle. So let me show you how to do that. I'm going to do it in degrees because that'll work nicer. If I go to degrees and I go inverse sine of 0.5, I get 30 degrees. Here's the problem. This is one of many answers that will work. Watch this. I'm going to check my work here. I'm going to do sine of 30. Sine of 30 should equal 0.5, right? Okay, it does. But 30 is not the only angle that would work. I'm going to show you some more. Sine of 150 actually also works. And I'll show you why in a second if you don't intuitively get it. Let me show you some more angles that'll work. Sine of 390 would also work. 390 means you went all the way around the circle an extra 360 degrees, but it still also gives 0.5. If I ask you to do the sine of negative 330, this means I go backwards around the circle. And so the biggest problem with solving one of these is this line right here. Your calculator, if you do this, will give you an answer. I'm going to say this a lot, especially to you guys over the next couple of weeks here. When you inverse sine, it will give you one of the answers, but there are a million answers that will actually work. Because all it means you got to do is just go around the circle a few more times. Okay? And so that becomes a problem, is that it gives you one of the answers you're looking for. And so I'm going to show you guys today some other ways for you to try to find all of the answers. So let's try some examples here. Let's say I asked you to solve for theta. This is a basic grade 10 level question. I'm just going to use this to work our way up. If I asked you to solve for this angle, you might say, okay, well, this side compared to the angle right here is the opposite. This side here is the hypotenuse. This side is the adjacent. Okay, I don't have the hypotenuse, but do I need it to solve this? Tan is equal to opposite over adjacent. So tan would be equal to 3 over 6. I just want to make sure I've shown you guys how to do this. How do you undo a tan sign? You use tan inverse is the word we use. What you're really doing is you're putting tan to the minus 1 on this side and on that side. And what ends up happening is a tan inverse next to another tan, it cancels it away. So what you have to do then is you have to tan inverse 3 over 6. I'll do it in degrees. If I inverse tan 3 over 6, we get, call it 27 degrees. You guys remember doing that from some point in your previous math courses? Okay. What is the difference then between this? Tan inverse 3 over 6 and tan of 30 degrees to the minus 1. Can you guys tell me the difference between these two? Because they both involve a minus 1. What does this thing right here mean to do? It means it's the opposite of a tan, and it's what you use to find an angle. Do you guys remember what putting a -1 afterwards really means to do? It's called the reciprocal. This guy right here really means you're finding the cotan of 30. Okay. I want to make sure it's clear the difference here. If you've got a calculator here, if you do this guy right here, cosine -1, and then you do something like, say, 8/9, this will find you an angle. Okay. But if you do cosine of 70 degrees to the -1, like this, that actually means to find secant. Okay, they're super, super similar, but there is a difference between the two. Okay, well, that's what I'm showing you on this slide right here. If you want to know what the angle is, you need to use the opposite of tan, which is tan to the -1, which we either call inverse tan or tan inverse. And if you do this sort of button right here, it will find you an angle. I'm going to focus on that a lot today in the next few days. It'll find you one of the angles that works. The problem is that there's sometimes more than one angle that fits. Okay, so let's try some examples here, and I'm just going to start by plotting just a coordinate point, and we're going to try to find the angle that works here. So now that I've built up some skills, if I ask you to plot the coordinate point 4, -3, hopefully you guys will agree that 4, -3 is roughly here. 4, -3. It's in quadrant 4. The angle that I want to talk about is all the way around here. Pac-Man. Anyways. However, although the angle is going to be like 300 something degrees, what we really want to focus on is the reference angle. So again, hopefully I've done a good job of building up some of these previous skills. The reference angle triangle is actually what I'm drawing in red here. It's like the leftover bit inside Pac-Man's mouth. Okay, we can plot some sides. One of the sides is 4. The other side is -3. Can we find the hypotenuse? How would you find the hypotenuse? Okay, you don't need to though. But you guys all know how you could. Does that make sense? Okay. We don't need to though. Because in order to find this angle right here, I'm just going to use one of either sine, cosine, or tan. Well, if I know this side right here is the opposite, and this side right here is the adjacent, or you could call this the y side and the x side, do we need to use sine, cosine, or tan to use opposite and adjacent? Tan, right? So what you'd say is that tan of your angle is opposite to -3/4. So if I want to find my angle, we need to tan inverse -3/4, and that should give me my angle. Here's the issue. If I inverse tan -3/4, it is going to give me an angle. And as I do this, it gives me -37 degrees. What your calculator is going to do is it's going to find the closest angle it can to 0. And it might actually go into the negatives. Here's the problem. That's not my answer. Because I know that my answer needs to be somewhere around 300 degrees. Because Pac-Man is what we're actually being asked for. We're being asked to find all the way around in the positive direction. So -37 degrees is basically going backwards this way. What's the positive rotation value then? Yeah, how'd you figure that out? Yeah, I think in this case here, I'm actually going to add 360. But yeah, I get what you're saying though. Because I had a negative on there. So the actual answer is 323 degrees. But the reason why we didn't get the answer when we used our calculator is your calculator found an angle that works. But you can go forwards around the circle. You can go backwards around the circle. You can go around the circle 7 times if you want. You know what I'm saying here? So your calculator will find you one answer, and it'll find the answer closest to 0, possibly going into the negatives, but it may not be the one that you want. Does that make sense? So you can't just trust your calculator anymore. You have to use a little more intuitive knowledge and go, okay, I know my calculator spit out an answer of -37 degrees, but 323 is what we actually want. That make sense? Okay, let's try another one. So hopefully you guys can see, especially you guys in grade 11, you can kind of see why I want to give you just one more lesson because I hope it kind of makes sense as to where all the rest of that stuff came from that I showed you. So let's plot this. Negative 12, negative 5 would be over here, give or take. Estimate for me in degrees what about the angle should be, like roughly. 10 degrees, 300 degrees, 200 degrees. Sure, that seems about right. I know it's greater than 180. I know it's less than 270. 210 seems reasonable. Okay, so I'm looking for the angle all the way around to here. That's what I'm being asked for as it rotates. I can plot some sides. This side's negative 12. This side's negative 5. Do I know the hypotenuse? Could I find the hypotenuse? You could. Do I need the hypotenuse to solve this question, though? I got enough. All I've got to do is tan inverse the opposite over the adjacent. If I tan inverse the opposite over the adjacent, it'll give me an angle. An angle. That's really important. It might not give me the angle I'm looking for, but it will give me one of many that fit. So if I inverse tan negative 12 over negative 5 over negative 12, it gives me 22.6 degrees. Is all the way around from here to here negative 22.6 degrees? You know what it did? My calculator calculated for me an angle as though it was in this quadrant right here. And it calculated an angle as though it was positive 5 over positive 12. Because you guys know how two negatives, when you divide them by each other, it makes a positive? Well, two positives divided by each other also would have worked. So the calculator calculated an angle as though it was this one right here. But that's okay, I can still work with it. It just means that this angle right here, the reference angle, is the 22.6 degrees, that's all. Does that make sense? So to calculate the actual angle, sorry Darian, you were a little bit further off, all the way to here is 180 degrees. And I've got to go 22.6 degrees more, so the final answer is going to be like, say, 202.6 degrees. Does that make sense? Let's confirm that. Let's take that angle. Let's add 180 to it. Now, again, you guys have heard my lecture about this is not exact, okay? Ideally, we'd find a way to do this in radians and make it be exact, but for simplicity's sake right now, I'm going to do degrees. If I were to take the tan of this number, it should equal that, which, if I make it a fraction, is 5 over 12. 5 over 12 is the ratio of opposites to adjacents. But it's not the only angle that does that. So although 202.619 does that, I bet you 202.6198649, if I added 360 degrees twice, if I took the tan of that angle, it also roughly gives me the same thing. You know what I'm saying there? So it's one of many angles that works. So hopefully I've done a good job of illustrating my point. When you inverse cosine, inverse sine, inverse tan, it will give you an angle. We have to make sure we figure out which one we're looking for. Okay. So let's try almost the exact same task now, only rather than me giving you a coordinate point, I'm giving you just a statement like this. I want us to calculate theta when it's 2 over 5. Well, I mean, the one-step answer is inverse sine 2 over 5. If I inverse sine 2 over 5, I get, let's call it 24 degrees. That's not the only one that works. Let me show you why. 24 degrees would be like roughly, I don't know, about this quadrant right here. Sine is opposite and hypotenuse. So if the opposite was 2 and the hypotenuse was 5, yeah, I can see that being basically 24 degrees. But I want to show you another place where you could have this work. In this quadrant over here, could I not draw a 5 right here and a 2 that's positive still? Okay, if it's 24 degrees right here, how far would it be all the way around here? Well, using like symmetrical triangles and ideas like this, if this is 24 degrees, isn't it still 24 degrees right there? So the angle all the way around would be 180 minus that 24 degrees. This number right here should also work. 156 degrees should also work. Let me prove it to you. If I were then to take the sine of this 156 degrees, it's going to equal 0.4, which is 2 out of 5. You want to grab the door for him? So this causes a bit of a problem for us because there is more than one answer. There's actually an infinite number of answers. I could have taken this number right here. I'm going to inverse sine 2 over 5. This answer works. That answer also should work. That answer should also work. You get what I'm saying here? When I added 360, I'm just going around the circle again. But if I were to add 360, let's say 78 more times, okay, there's a very large angle. But if I were to sine that very large angle, I hope this works out properly, it's still 2 over 5. So the point I want to make here is that when we're being asked to solve things, there's actually an infinite number of answers because you can go forwards around the circle some more. You can go backwards around the circle some more. So I hope it's on my next slide here. Yeah, that's what I've got right here. On this slide right here, I've got the idea of multiple solutions. When you are solving backwards for an angle, there's often more than one answer. Is everybody okay with that idea of how we're going to have more than one answer? Does that make sense to you guys? It's frustrating, but does that make sense what I'm saying here? Okay. So I've got listed down here 2 different ways that we deal with this issue. Okay. Again, if you guys are in my 20 level class, just watch this. I'm not testing you on this. Okay. If you're in my 30 level class, this is totally what we're testing you on though. Okay. The 2 ways are we either write what's called a general solution, which is an encompassing way of trying to find a way to write every single possibility. The other way is what we do is we restrict the domain so only a few answers fit. Let me show you a couple ways that we do this. So let's try another example here. Can I skip the other one we did there? I feel like you guys are getting this. So let's skip that other example. Let's try this one here. Let's say that I tell you that sine of theta equals 1/2. What you could do is go sine inverse of 1/2 and get me an angle. So, anybody already beat me to that? What's the inverse sine of 1/2 in degrees? This is one angle that works, but it's one of a many, many, many angles that would work. I'm going to draw a quick little graph right here. If 30 degrees is supposed to be one of the answers, if I were to plot 30 degrees, it should be in this quadrant here. There's 30 degrees. The opposite would be 1. The hypotenuse would be 2. Not that I need it, but hopefully you guys know what the other side is. You guys remember this triangle? It's root 3. Is this the only location, though, where I could have a positive 1 and a positive 2 sitting over here? Oh, there's a second location. We actually learned this last day according to something called the cast rule. The cast rule helps you kind of know where this works. Everybody is positive in this quadrant right here, but sine is, this is a positive number. Sine is also positive if you go in this quadrant right here. Because what you'll end up with is you'll put a 2 right here. This will still be 1. This will be just negative root 3. But if we're talking about sine, do I care that this side is negative root 3? Sine's opposite over hypotenuse. Here's your opposite, it's still 1. Here's your hypotenuse, still 2. Does that make sense? Why could this quadrant right here not work? You'd have a 2 here, right? But then this would be a negative 1. Well, then sine would be opposite over hypotenuse. Hang on, that would be negative 1/2. And we need it to be positive 1/2. So, like, this quadrant's out. So, okay, so one of my possible answers is 30. I already did this one for you guys, actually. Another possible answer, all the way around to here, is 150. Does that make sense? Because this is the exact same triangle, only there's a 30 on this side here. So if here is 30, the rest better be 150. So as I answer the questions I posed here, what quadrants could the terminal angle lie in? Quadrant 1 or quadrant 2. It could have been here or here. Can I change this just for simplicity's sake right now? Let's make this degrees. You guys can convert to radians later if you need to. But just for the sake of this question here, what is the measure of theta? Well, it's 30 degrees, or it could have been 150 degrees. But let me give you some more ideas. It also could have been 390 degrees. How did I get 390? Yeah, I went here all the way around the circle, some more. You know what else I could have done? I could have done 150 plus 360. I could have done 510 degrees. You're going to see how I got 510 degrees? I would have gone to here all the way around the circle. I could even have done negative 330 degrees. So here's the problem. This could keep going in both directions. So one of the ways we have to solve this problem is we use what's called a general solution. Okay, or at least you guys are going to do a general solution. You guys don't care about this. So here's how you write it. It's going to make sense once I show you. Here's the solution. It's going to be 330 degrees or 150 degrees plus or minus 360 n. This is how you write a general solution. 30 degrees or 50 degrees plus or minus 360 n. I already see a couple of you nodding. Does it make sense how this works? 30 degrees, you could add 360 to it once. Or 30 degrees, you could minus 360 from it once. This n right here is like a natural number. It has to be like 1 or 2 or 3. So what I'm saying is you could go around the circle 1 extra time. You could go around the circle 2 extra times. You could go around the circle 3 extra times. Does that make sense? The plus or minus, meaning that you could go forwards around the circle or backwards around the circle. Okay, that's how you write a general solution. If you had to write it in radians, by the way, 30 degrees, I just happen to know these ones, is pi over 6. 150 degrees is 5 pi over 6, if you can convert them. And then when you go around the circle, you'd go around the circle 2 pi n times. That's how you'd write it in radians. Because 30 degrees is pi over 6 if you convert it. 150 degrees is 5 pi over 6. But you still go around the circle either in the positive or the negative direction. But in radians, all the way around the circle is 2 pi now. That's all. So that's one way we solve this problem. We write a general solution. So why don't we try the other way of solving these. The other way we solve this is we restrict the domain. You see this little like quantifier afterwards here? Or this one right here? What this means to do is, all I want you to do is solve for the solutions in those parameters. So even though we know that there's a million solutions out there, only solve for the ones that are within that section. You know what I'm saying here? So let's try the second one here. I want us to solve for where tan of theta equals root 3 between 0 and 2 pi. Because that was one of the more challenging ones here. The reason why I want to point this one out is that this one does not appear to be a fraction. See how this one right here was a fraction? It actually is a fraction. Josel, you got it. It's root 3 over 1. And so what I'd like to do is I'd like to start plotting, well, where on a grid could it be root 3 over 1? Well, this quadrant right here, you could have the opposite be root 3. You could have the adjacent be 1. What would the other side be? You guys remember what angle? Not 45. This one's actually 60 degrees right here. However, I didn't want it in degrees, though. We wanted to solve it in radians. So are you guys getting more and more familiar? Do you guys remember what 60 degrees is in radians? It's 1 pi over 3. Yeah, I mean, if you have to do it like this, 60 degrees times by 2 pi, divide by 360. Kind of cancel those. Don't use pi. But, I mean, if you're getting better at this, it's actually pi over 3. So there is one of my answers. Pi over 3 would work, which is 60 degrees. However, is that the only answer between 0 and 2 pi that fits? Which other quadrant would this fit in? Good, you got it, Joe. C-A-S-T. You could also have one of these be in the third quadrant. Now, in third quadrant, it would actually be negative root 3 and negative 1 and 2. But when you're talking about tan is opposite over adjacent. The two negatives would cancel each other. Okay, well, if this was the first third of pi, in this quadrant it would be the second third of pi. Flat across would be the third of pi. Right? 180 is always 1 pi. Right? Well, this quadrant right here would be the fourth third of pi. There's my second answer. 4/3 of pi. Are there more answers than this? Within my parameters? No. Okay. Does that make sense what I'm saying though? So that's what makes solving trig equations so challenging, is that when you're going one way, there's just one answer. But when you're solving for the angle, there's so many answers that we have to find a way to narrow it down a bit. So the two ways we do it are we either write what's called this general solution right here, or we write like a quantifier afterwards with like a counter, and you just keep going around the circle more and more. That's one way of doing it. Or the other way of doing it is I will narrow down under what conditions you go, and then usually there's only like two answers there. Okay, here's an old diploma question. So again, this is not, if you guys are in my grade 11 class, this is not your curriculum officially. So if this is still a little beyond you, that's fine. Please don't freak out. But hopefully this does make a little bit of sense at least. My question is, we want to solve this. Is it written as a fraction over here right now? Well, it is if you write it over 1, but see how there's a 2 sitting in front? Any idea what you can do with that 2 on the other side of the equation? Yep. So divide it. Okay, it's actually sine of theta is root 3 over 2. Okay, next thought here. Let's plot where on this grid sine of theta can be root 3 over 2. It definitely can be in this quadrant right here. Sine is equal to the opposite over the hypotenuse. Do you guys remember what the other side is on this triangle? Perfect. Okay, now that is one of the triangles that will fit. However, there's definitely going to be a second triangle that works, and if you know your cast rule, the other quadrant in which sine is positive will be in this quadrant here. It'll still have a 2, it'll still have a root 3, but now it'll be negative 1. But sine doesn't care about the fact that that's negative 1 or positive 1, because sine is only opposite and hypotenuse, and this is the adjacent. Next thought, we need to now figure out what this angle is right here by just knowing your triangle. That part is grade 11 curriculum, by the way, and it's 60 degrees in this quadrant here. Okay. I promise you, the more you do this, eventually you're going to memorize this. 60 degrees is pi over 3. And eventually you're going to recognize this, because really, if I broke this up into like a here's the full horizon, here's the first third of pi, this is the second third of pi, here's the third of pi. Does that make sense? So this answer right here was the first third of pi. The other one, by the way, would be the second third of pi. Now, that probably is enough to answer the question, because here is one that involves the first third of pi, here's the one that involves the second third of pi. But do you guys understand what this little thing here means then? With a general solution, in theory, you could have gone around the circle an extra time. Well, that's what the plus or minus 2n pi means, is that you just went around the circle positively an extra full time. You guys follow that? Cool. Okay, so I think I've only got a few slides left here. 2 more slides? Just this one here and this one here? Okay. So let's try some last examples. Again, for you guys in my grade 11 class, this is not what I'm going to ask you to do on any tests, okay? But, I don't know, give me some feedback. Does my whole 3 set of lessons make more sense going all the way to this point? I hope. I hope. So, our goal is now to try to solve an equation involving sine, cosine, or tan. Okay. So let me show you how to do this. It still involves some old-fashioned algebra skills. Like, for example, right here, what we need to do is we need to make it equal to a ratio. It's not currently equal to a ratio. It's actually equal to 0. But watch this. What if I were to add 0.5 to the other side? What you'd be left with then is 0.5 cosine theta equals 0.5. Does that make sense? Then I would divide by 0.5. And I would be left with cosine of theta equals 1 over 1. Okay. Why don't I go to my calculator now? I'll do it in degrees just to make it simpler right now. What we could do is we could inverse cosine 1 over 1, and this should tell us an answer. 0. Okay, let's think about this for a second here. 1 over 1. What is cosine supposed to be equal to in terms of like the two sides compared to each other? The top one is supposed to be the adjacent, and the other side is supposed to be the hypotenuse. However, it's really hard to draw a triangle in which, like if I were to try to draw this triangle, here's my angle here. If I draw my hypotenuse with the side of 1, and I draw my adjacent with the side of 1, it's not really possible. So I want to change our definition though. We learned a while back ago that rather than it being pardon me, rather than it being a and h, we can also replace them with x's, y's, and radiuses. So I believe this one was supposed to be x. Sorry, that's supposed to be x. And this is supposed to be r. You remember talking about that? So I'm going to plot a point on the unit circle where my radius is 1 and my x value is 1. Now this may seem kind of silly, but that point is going to be right here. Here, my x value is 1. My y value, by the way, is going to be 0. What's the radius of this bit right here? So 1. How many angles have I rotated through? I haven't. Which is why, when I did the inverse cosine of 1 over 1, it gave me an angle of 0. It's kind of trippy. It's kind of weird to wrap your head around that, because it's really not a triangle, actually. There is no triangle being drawn here. What I have here is I have a x value of 1. I have a y value of nothing, because I didn't move it up at all. But my radius is still 1, right? Because as I'm going around the circle, if I went around the circle, wouldn't the radius still be 1? So if I ask you how many degrees did you rotate through for you to get to there, the answer is you didn't. So to solve this equation, I shouldn't have started with a trick one on the first one, I don't think. But the answer is a 0 would do it. Okay. When would the next time this would work be? 360, which would be 2 pi. And then 4 pi, and then 6 pi. Those would be all the answers that work. Okay. Chances are, because I didn't have the right way of doing it, it probably should have had those little bars underneath it there. Because usually you include 0 and you include 2 pi. So if I were then to ask you in this parameter right here, which answers would work, that and that wouldn't count because that's going around the circle too many times. But like these two would be some answers that work. Like 0 should work, and 2 pi should work. Right? And I'll prove it to you. If I go 0.5 cosine of 2 pi, and then I minus 0.5, and I do it in radians, not graph, that's not right. This should equal 0. Let's try another one. This guy right here is a bit more challenging because what we've done right here is I put a 2 in the corner. What this really means is that you're squaring it. In a way, this is actually a quadratic, okay? Well beyond grade 11 curriculum, by the way. Please don't freak out. But in a way, this is like 2x squared plus x equals 1. So there's a quadratic kind of merged into our trigonometry. You guys get what I'm saying there? How do you solve quadratics? Nope. You're almost done. How do you solve quadratics? What's the basic way of solving quadratics? Make one side equal to 0, yeah. So here's how you're actually going to solve this. You're going to make it 2x squared plus x minus 1 equals 0. And I'm going to factor this guy. So to factor this, I'm going to look for numbers that add to give 1 and multiply to give negative 2. And those numbers are 2 and negative 1. Okay, because of that, I'm going to have 2x squared plus 2x minus 1x minus 1 equals 0. Let me know if I lose you on the factoring part. Or I factored it. Can you guys handle the factoring bit? Okay, but here's the thing. It wasn't x. It was actually sine theta. So like what I really was doing is every time that I had sine theta, I just wrote x. I wrote that because I'm more familiar with working with x's than sine thetas, but really this should have been sine theta. 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 Now I'm not going to rewrite them all in as sine thetas. I'm just going to go down to the very bottom and do this. I'm going to say it should be 2 sine theta minus 1, and it should be sine theta plus 1 equals 0. Well, I can actually solve this bit right here. What this really means is that sine of theta needs to be equal to 1/2, and this one right here means that sine of theta needs to be equal to -1. In the same way that when we solve quadratics, we tell you that x equals 1/2 and x equals -1, I solved it all as though it was a quadratic in x, which I know all you guys can do, because even you guys in grade 11, this is like our big focal point in our unit, only the twist here is that rather than using x everywhere, it actually was supposed to be sine theta everywhere there was an x. That's all. Okay. Now let's try this. Hey, this guy's equal to a fraction. I can plot that. Where is sine of theta supposed to be equal to 1/2? Well, the 1 is supposed to be your opposite, and the 2 is supposed to be your hypotenuse. So that can be in this quadrant right here. The 1 could be my opposite. The 2 could be the hypotenuse. The other side is √3. Not that I need the other side, but the other side is √3. What angle is in the corner right here? It's 30 degrees. Yeah, if you know your triangles, this one here is 60 degrees. This one's 30 degrees. Hey, I found an answer. 30 degrees should work. Let's try it. I'm going to go right back up to the very top here. I'm going to try 30 degrees in here. I'm going to go 2 times the sine of 30 degrees. I'm going to square it. The way this notation works is that although we put the squared in between the sine and the theta, it actually means to go afterwards. It's just our way of writing it. And then I need to add sine of 30. And then if the sine of 30 is correct, this should equal. It wouldn't have equaled. Okay. I did it right. Does that make sense? I found an answer that works. But I use that keyword in there again. I found an answer that works. Is that the only answer that will work? No, there's actually, this is what makes trig really suck, is that you have to find all of the answers that work. So I'm going to now look for another answer. Is this the only quadrant where sine of theta could equal 1/2? Over here would have worked, because you could have put a 1 here and a 2 here. It would have been equal to -√3, but that doesn't matter for sine. Sine doesn't care about the this value right here. What would the angle all the way around here be then? Daniel's right, yeah, 150. Because you put a 30 here in the corner, the leftover bit is 150. Again, we should be able to check that. So I'm going to do 2 times the sine of 150. Then I'll square it. Only my calculator froze. Squared. I will add the sine of 150. And then if I did this right, again, this should equal 1. Maybe you think, hey, maybe everything equals 1. Well, let's just try another random number. Let's try the sine of 160. Just to be sure. Okay, so not everything equals 1, right? Only certain numbers do. Okay, now in this sort of area thing right here, are there more answers that could work? Give me another answer that could work based on like sine of theta equaling 1/2. 390. Because that just means you want to surround the circle another time, right? So maybe the best way of us writing this is it's going to be 30 degrees or 150 degrees plus or minus 360 n times. That's a good all-encompassing way of writing it, is that if I were just to keep going around the circle more and more and more, that should still work. So this is a good all-encompassing way to account for just this half right here, though. Okay, next part, though. I also need to try to figure out where sine of theta equals -1. Now, this one's a bit more challenging, but I already did one like it right above it. -1, if I wrote it out, it's really -1/1. And sine is opposite over hypotenuse. But it really doesn't make sense for me to draw a triangle with the opposite and hypotenuse the same side. So let's use the other definition. Let's say that your opposite is your y value and your hypotenuse is your radius. Let's use that instead. Where on this grid would I find a y value being -1 while also having my radius be 1? Well, -1 in the y value would be like down here, right? And so the location I'm looking for is actually right here. Because what I've done is as we've started rotating our circle around, our radius was always 1, but right here, my radius is 1, and my y value is -1. So if you rotate it all the way around to here, how far do you have to rotate to make that happen? Yeah, 270. All right, one more time. Let's try that. If I were to then try the exact same equation, sine of 270, square it, add the sine of 270, it should equal 1. Okay, a couple of thoughts here. Again, don't worry about this, okay? I'm not going to assess you on this, okay? Because it's beyond, you guys need to practice the skills that work up to this, okay? But hopefully you can follow it. So I'm really talking to you 7 right here. You're going to dislike this part of trig to some degree because it's like combinatorics. There's not a lot of work to this, okay? Most of it's logic and reasoning. Once you find one answer, often what I'm just doing is I'm drawing like a picture and I'm trying to figure out like, well, where are the other answers? Where could they be? You get what I'm saying, though, where there's not a lot of work to it? There's really no show your work in trigonometry. There's more of a find one of the answers and then use reasoning to figure out where the other answers could lie. Make sense? Right. Why don't we try one last example and we'll call it a day. Let's do A, and then I'll be done. What's the one little tweak I threw on this example here that's slightly different? Yeah, can you guys see that? I threw a 2 inside here. Okay. Again, doesn't matter to you guys. This is next year. But you may as well see it just once now anyways. We do the exact same stuff we normally do. Well, what I'm going to do is I'm going to figure out, ignore the fact that there's a 2 there right now. How would you solve where cosine theta equals 1/2? Well, what I would do is I would say to try to plot it somewhere. Or I could even inverse cosine it. Cosine of theta equaling 1/2 means I need the adjacent to be 1 and the hypotenuse to be 2. So that happens right here. That would work. The other side would be √3, and the angle in the corner right here would be 60. However, what we've actually figured out now is that 2 theta equals 60 degrees. Because this thing right here was not theta, it was 2 theta. So how do I find what regular theta is? Yeah, that's it. So 30 degrees. Let's try it. Cosine of 2 times 30 should equal 1/2. That's not the only answer that's going to work though, right? There is another location where we could draw a triangle like this. According to the cast rule, C-A-S-T, everybody's positive here, but cosine should have another positive value down in this quadrant here. This side's 1, that side is still 2. Okay, this side right here is -√3. Do I care that this side is -√3 though when we talk about cosine? Well, no, because this side is the opposite, and cosine only cares about adjacent and hypotenuse. So all the way around to here then, is going to be 300 degrees because there's like 60 degrees left over. Okay, but it means that 2 theta was equal to 300 degrees. So when you divide by 2, actual theta would be 150 degrees. So just to prove it, and then we'll call her a day. Cosine of 2 times 150, this should equal 0.5. And it's one of many answers that will equal 0.5. Last thought. I actually asked for a general solution, though. Okay, well, general solutions aren't that hard. You just do this. 30 degrees or 150 degrees plus or minus, and you just got to go around the circle. However, we're not going to go around the circle 360 times. Because you know how we had to cut this angle in half to make it 30? And we had to cut this angle in half here to make it 150? Rather than it being 360 degrees n times, you have to cut that angle in half too. Does that make sense? Because we're talking 2 theta, not 1 theta. So your next answer is not 360 away. It's actually 180 degrees away. So last thought, then I'm done. I keep saying last thought, then I'm done. 30 degrees works. 150 degrees works. What's the next angle that I should try? 210. Make sense? Because 30 degrees plus 180 would give me 210. So I'm just going to confirm that, then we'll go. If I do cosine of 2 times 210, that also equals 0.5. So long story short, if you ever see a 2 theta sitting inside here, it's actually really easy. You just solve it like you normally do, and then when you get your answers, you just divide them all by 2. If you're doing a general solution, divide the 360 by 2. Okay, that was 4 really intense days of trigonometry. Thank you guys. This is the first time I've ever tried teaching it like this. I mean, I still need to see how you guys do on stuff, but I feel like as I was teaching you, this went way better than I've done in the past. Do you guys feel like you kind of understood what I was talking about? A little bit? I know you guys, you haven't had as much experience, but... Okay, so here's what I want to do. Next week, we're just going to do work time. Okay, you need time to digest this and try this. So I will change the schedule, but you guys for sure, I'm going to give you all 4 days next week to work. Okay? There's no school next Friday now. Okay? You guys at 30-1, I do need to teach you 3 more lessons. You guys are 3 lessons away from being done, by the way. Did you guys know that? We are done math curriculum in 3 lessons. So I may need to teach another lesson on, like, say, Wednesday or Thursday next week, but we're not going to do a quiz, okay? Sound good? You guys good? Okay. We'll see you guys later. Have a great weekend, guys.